Hi, everybody. So I am very happy to welcome you to this mathematics and industry meeting, which is devoted to mathematics and movement in sport. So this event is part of the week Mathematics and Movement, which is a national week. And I would like to remember that the main institutions involved in this organization are so AMIES, which I am representing, which is a French agency for mathematical and industry, and the SMAI, which is a mathematical and applied mathematics and industry society, and also the CAMS, which is a center for analysis of mathematics. Of social mathematics. So during this morning, so we shall have some presentations showing how the technology, which is much involved nowadays in analyzing movement, can help, for example, to optimize performances in sport. But also to which kind of implication on real virtual reality it has. And I also would like to mention some quite recent example, which was a collaboration very recent between some mathematicians and some small startup, which is InEmotion. And this company wanted to construct airbags for motorcyclists. And this kind of airbags exist, for example, for skiers or for horse riding. But for motorcyclists, it's much more complicated because you see when a motorcyclist takes a turn, the boundary between a nice turn and a fall is quite tiny. And they needed to have more technology in it, and a lab in Grenoble did some work based on machine learning in order to analyze the parameters, and finally they succeed to build this airbag. So this is just an example to show how mathematics are involved in the analysis of movement and sports. Okay, so I would like to thank also the organizers, so Amandine Naftalion, Florence Hubert, Frédéric Richard, Stéphane Cordier, and Thierry Orsin. And that just say, okay, so enjoy this morning and have a nice talks.
Mark King, who's coming from the University of Loughborough in England. England has a tradition which is much stronger than France to involve scientists at a very high level in sports competition. And probably the University of Loughborough is one of the best in the world in terms of matching scientific experiments with a sports competition at a very high level. And Mark doesn't come from a mathematical background, but more from a biomechanical background, and so he will be quite at ease to speak about movement in sports. And I think you're a specialist in cricket yourself and badminton, so welcome to introduce us how English sciences help sports better than French science, and so we'll try to learn something from you.
University in England, and yeah, I'm a biomechanist, so I did a mathematics and sports science undergraduate together, and then I combined those together into something called biomechanics. So my sport is badminton, and I thought let's start with a video of someone who's a lot better than me performing the jump smash in badminton. And if we look at this, is this optimal? He's a top 10 player in the world, England's #1 at mixed doubles, and I've converted a court here so I can do some biomechanics analysis. But as a scientist, I'm interested to say, is that optimal? So I can look at it using 3D motion analysis. So measuring actual performance is easy. But it's not so easy to say, how could it be better? So is this optimal? And so what I'm going to try and show you in today's presentation is that, not from an experimental point of view, but from a theoretical point of view using mathematics, how we can understand optimal performance. What would I say biomechanics and motor control is? Well, it's using mechanics to understand and explain things. And the understand is the really important thing. And I'm looking for things that are important, factors that are important. And from my perspective, I make it very simple. It's either improving performance or minimizing injuries. So I'm going to try and give you examples from both of those this morning. And my philosophy would be, in elite performance, there are some factors that are critical. But there's lots of other things that aren't so important. And they might be down to individual variation, how a coach has coached that particular athlete, but they don't really matter. But what are those factors that really do matter? Clearly, we can collect things experimentally, we can understand things theoretically, and of course, the best solutions is one where we combine both of those. But in the short time I've got this morning, I'm going to focus on things from a theoretical perspective. So I'm going to give you 3 examples. Tumbling in gymnastics and springboard diving, and looking at optimal performance. And then a different example from racket sports, from tennis, some work we did on the one-handed backhand ground stroke, linking that to tennis elbow injuries. To give you a flavour of how we can use theoretical analysis to understand movement. So here's a double layout somersault in gymnastics, performed by a top 10 gymnast some years ago. And I'm ambitious, and at Loughborough we like to maximise things, so instead of 2 somersaults, could he do 3? What would it take for him to do 3 somersaults? Well, I clearly can't take this gymnast and do that, because it might end in tears, so I need to do something theoretically. And the 4-stage process I'm going to talk about in each of these models is I'm going to build a model, a computer game of that athlete, if you like. I'm sure you've all played computer games at some point. And then going to make that model specific to the individual, in this case the gymnast. Then going to show that the model works before optimizing performance. Well, the critical phase in tumbling is the final takeoff. And if we take that position, we can simplify the body into 5 rigid segments. They're the key segments that are moving and the key joints. Then can model the strength of the gymnast by 4 torque generators here. So the muscles produce a force with a moment arm that produce a torque, and the 4 key joints are there. Also, the tumbler doesn't tumble on a hard floor, it's at an elastic surface, so I need to put some springs in there. At that point, the model could represent any of you. It could be any of you in the room, but I want it specific to the gymnast we've just seen in the video, so I determine parameters that are individual for him. The mass and length of the segments, that's easy. How strong he is, so I measure him on a dynamometer, what his strength is, and also some characteristics of the tumble track. So at this point, the model, in theory, represents the gymnast. But I need to have some confidence that the model is working. So I do some optimizations to say, can the model do what the gymnast did to start off with? So at the top, we've got the video of the actual performance, and the simulation at the bottom starting in the same position. So the same initial conditions. And if we play the video, we can see that the model is able to do what the gymnast did. So I've now got some confidence that the model works. So from now on, I don't need the real gymnast, I only need the model to now investigate what's possible. So if you remember, my original question was, could he do 3 somersaults instead of 2? Well, maybe his technique isn't very good. He's an elite gymnast, but maybe if he just tried a bit harder, he could do a bit better. So I said to the model, do a bit better. What can you do? So I ran an optimization. The computers would try to maximize rotation in flight. And instead of 2 somersaults, the model did 2 somersaults. The model isn't able to do any more. Well, that was quite reassuring, because this elite gymnast had spent 10 years training. Would I expect my model to be able to do any better? Probably not. Or if it did, I probably wouldn't believe it. So this shows, I think, that the model's working. But it still hasn't got me to 3 somersaults. So what's the next thing I could do? Let's make the model really strong. Okay, so a 50% improvement in strength everywhere. Might take the gymnast 100 years to achieve this, but I can do it overnight with my model. If I make the model really, really strong, what happens? Well, instead of 2 somersaults, we get, we get 2.5 somersaults. He only does this once. This clearly isn't 3 somersaults. So strength isn't the limiting factor in tumbling. So I put the strength back to what it was at the beginning. And then said, okay, well, if I look at tumblers versus gymnasts, so my athlete was a gymnast, if I look at tumblers, they can run up considerably faster and still do this movement. So if I put my model running up a bit quicker, 50% increase, which is about the limit of what tumblers can do, optimized performance, instead of 2 somersaults, we get 3. Magic. So I found a solution where we can do 3 somersaults. So I presented this work many years ago, and of course I didn't really know if this was realistic. Nobody in the world was doing this. But then someone sent me a video from Russia. Someone runs up really fast, and they did 3 somersaults, or 2 3/4, and they land on their head but rotate very fast. They just get round. So here I've predicted, completely independently of what limiting movement is, and then here's someone doing it. Runs up really fast and just achieves it. We'll move on, else he'll get a headache. So that's my first example, tumbling, showing how I can use computer modeling to predict optimal performance in sport. My second example is similar, but it's springboard diving, so it's still another gymnastics movement. Well, here's a young elite gymnast performing a forward dive pike, and then, so that's a dive with not too much rotation, and here's one with 2.5 somersaults. How can I model this activity? Well, I go through the same 4-stage process. Build a model that's specific to that movement, determine parameters, show the model works, and then see what we can get. So this model is a bit more complex. There's more joints. This was done a bit later. Got a springboard that depresses about 90 centimeters, so we've got that in there. And we've also got more torque generators here. So we've got flexors and extensors now at each of the joints. Again, I go through the same process, make the model specific to that individual, and then show that the model works. So here's the forward dive pike, able to closely model what the person can do, including the splash. And the same for the 2.5 pike dive. So if I now use this model, I can investigate what's possible. Well, I can't make this model run up faster, so I'm restricted to the same sort of starting position. So it's probably of no surprise that with optimum technique here, for this diver, we can only get a small amount increase in rotation. So again, supporting the notion that these sort of models can accurately represent human movement. So 2 examples from rotation, if you like, around performance. My last one is closer to my heart in terms of racket sports, and this is tennis. So this was some work we did a few years back, where lots of players were getting injured at the elbow. They were getting tennis elbow, and this was associated with the one-handed backhand ground stroke. So we wanted to investigate what could we do to mitigate or reduce the loading at the elbow. Could we change the properties of the racket to reduce this? So we went through the same process, but this model is a bit different. It's a bit more complex, built with a slightly different package, and only really simulated the trunk and the arm and the racket. The parameters were again made individual to the athlete and included the racket as well as the arm. So we had point mass locations on the racket where the ball could locate, as well as the properties, elastic properties of the racket. And here's what the matching simulation looked like. It slows down during impact because we've got a shorter integration period just so that we can model accurately that impact. But we get a nice, accurate simulation of what the person did. So we take that matching simulation that accurately represents what the person did and said, we can now make some alternative simulations. What would happen for different characteristics? So I can perturb where the ball hits on the racket face, along with then changing properties of the racket and also how tightly we hold the grip. Well, the key measure, if you like, or output of loading on the arm is the flexor extensor torque at the wrist. And for a center impact, that's what we get. We don't get very much. If the ball hits in the center of the racket, everything's in equilibrium and everything just works. But if I perturb where the ball hits on the racket, so the person thinks they're going to hit the ball out of the middle of the racket, but then I move where the ball hits on the racket, they hit off center, then I get a huge increase in loading at the wrist. If they hit at the top of the racket, they're going to get a large torque in one direction. If I hit at the bottom of the racket, I get a large torque in a different direction. So I get a moment arm produced due to the ball hitting off center, and that forces the wrist to move and therefore produces eccentric contraction of muscles. And this is what it looks like. So this is the ball hitting at the lower part of the racket. It forces the racket to twist, forces the wrist to flex, stretches the muscles, and causes the increase in loading. So for that perturbation, is there anything we can do to the properties of the racket to change it? So this piece of work was sponsored by a racket manufacturer who hoped that it would, and then they'd sell lots of rackets, but this is what we found. So we change these properties, and we're trying to minimize that torque at the wrist. So our starting point was our off-center impact, where we had an 8.2 Newton meter loading of the wrist extensors. Could we mitigate and reduce that by changing the properties? And the answer was no. So if we changed the properties of the racket or the moment inertia racket, it made almost no difference. If we changed the stiffness of the racket or changed the tension in the strings, again, very similar. And the only thing that made a slight difference was not holding the racket as tightly, but short of letting go of the racket, we really couldn't make a practical difference. So the racket didn't work, unfortunately. So I've given you 3 examples there of how we can use modelling to understand movement in sport. What I'm going to do now is just summarise where I think we are. From a performance perspective, we can understand movement in a variety of sports, and I've just given you some examples just now. And primarily this often feeds into coach education within the UK. Where's the future going with this? Well, we've started with some sports, and some of the work I do with England cricket is using models to influence coaching on an individual athlete basis. So we build a model of this specific athlete and then use that to help inform the coach of how to improve the performance of the athlete in front of us. So that is starting to happen, but it's not commonplace yet. From an injury perspective, we're starting to understand the factors that affect loading, But impacts are tough to model, and things like ground reaction forces and passage of that force through the body is still to be improved, I would say. But where might we get to? Well, with increased model complexity, I think we can start to minimize injuries through modeling. I hope that's given you a flavor of what we can do with modeling. Thank you very much.
Thank you very much for this very nice talk. We have time for 1 or 2 questions, very quick questions.
Nice talks. Thank you. I would like to know, okay, when you optimize, what kind of optimization technique you use? I mean, in the first example, you said, oh, it doesn't work, but what is the meaning of it doesn't work? Is it because you have some local minimizers or some?
Okay, so we try and parameterize the solution space by using essentially torque actuators to drive each of the torque generators. So we use a small number of parameters for each torque generator. So we have about 7 or 8 parameters which defines when a muscle gets switched on and when it gets switched off. We then use a simulated annealing algorithm to vary those parameters within realistic bounds to then maximize or minimize an objective function. So in this case, the first one, tumbling there, it would be to maximize rotation.
I have maybe a question concerning pedagogical tools, is because your model could be thought as a way to learn how to dive, for instance, for people who start learning and make mistakes to understand what they do wrong. Is it really used like this, or have you tried developing this direction?
I think that there's a whole new area of work that could be done around that to learn what's the best way to learn a new skill, from the progression from a young child to an elite athlete. We haven't done that yet. All we've done at this point in time is looked at what does the solution space look around optimal performance, how the progression and skills to learn from a youngster to someone better is an interesting area, but not one we've looked at yet.
Another quick question in the audience? Or? Okay, so we skip to the next talk. Thank you very much, Mark. Anyway, at the coffee break, we'll have time for more questions if needed.